Okay, it appears now that we are recording. So this is example 5 from page 402, where we want to look at the population, at pregnancy gain, and whether or not samples that we see are within expected ranges or beyond expected ranges. And we're going to start to work towards hypothesis testing. So I'm going to use the highlighter to sort of denote things, which is our population mean mu is equal to 30 pounds, and the standard deviation is 12.9 pounds. So if this was normally distributed, which we are going to treat it as, this would mean that in the population, we know that for normal distributions, roughly 67 to 68% of observations will fall within one standard deviation of the mean, and 95% will fall within two. And so, just to briefly interpolate, we would expect that 67% of our pregnancy weight gain would be between 27 and 53 pounds, which is 17 and 43 pounds. 30 minus 12.9 and 30 plus 12.9. We know that 95% of our observations would be between a 4-pound gain, which is 30 minus roughly 26, and up to a 56-pound gain, 30 plus 26. We have, in our case, a sample of 35 patients. They have we have an observed sample of 30 increase of 36.2 pounds, and that's our X bar. And what we want to know is, is that what we want to know is this sample within we want to set up a hypothesis basically that is X bar significantly different from the population mean. So we're going to have a couple of things. One is we need the standard error of the sample mean, and that's given by this equation here, which is that sigma X bar, which is the standard error of the sample mean, is the population standard deviation, 12.9, divided by the square root of the number of individuals or number of observations or individuals in our sample, which is 35. And then that equals sigma over the square root of n algebraically. Now, to estimate a z-score, the z-score is going to tell us, are we close or are we not close? And so high z-scores indicate that we can reject the null hypothesis. Our hypothesis is stated as X bar is equal to mu, or X bar minus mu would be equal to 0. And I'll do you may ask about that in class tomorrow, so I'll do the hypothesis more formally tomorrow, please. And then it's divided by the sample of the standard error of the sample means. So then what we have is the sample mean, 36.2 minus 30. And then we're just going to bring this down, the 12.9 divided by the square root of 35. And that gives us a difference, 36.2 minus 30 equals 6.2. And then we have the 12.9, and the square root of 35 is 5.92. So then that equals 6.2. 12.9 divided by 5.92 is 2.18. And 2.84. Yes, I can actually talk. 2.84 then, moving along, is our estimated z-score, as I have it expressed here. And we're going to calculate that or evaluate against our what we would call the critical value for z, or some people might refer to it as the threshold of z. I prefer the critical value, but it's actually your choice. So we go to the table in the back, tables and formulas, and Sullivan, and I believe it's table 5. And if we want to set the critical value for z, we have to go back to our issue of alpha. Alpha is going to equal 0.05. And what that really says is that we have a 95% confidence interval, or that we would expect only that in 19 out of 20 samples, 95%, we want to have a range that would be where we want to know what range that would fall in. In 1 out of 20 samples, we would fall outside of that range by chance alone. So just by statistical sampling, we would be beyond that. The 95% confidence interval, you'll notice, is 1 minus alpha, which is there. The critical value, and this is something you can always relate to when we're using the normal distribution to evaluate a sample, the critical value is 2.96, and that's for z. Z equals 2.96. Our estimated value is 2.84. 2.84 is less than 2.96. I'm going to get rid of that little stuff at the end. So we failed to reject the null hypothesis that x bar, our sample mean, is equal to the population mean, which is equal to 30. So basically, even though we have a sample difference of 6.2, we would say that it's not statistically different from the population mean of 30. And again, the null hypothesis is that the sample mean equals the population mean, and we fail to reject that hypothesis. So that walks us through this problem, and I hope